Hello everyone, I'm Sourav Saha. I'm a PhD student at Indian Statistical Institute, Kolkata. So I'm going to present our work on modifying evaluation measures to deal with ties in ranked list. So ties can be present in ranking. So we observe ties in ranking in three applications. So one is knowledge gap recognition by recent work, Sun and Bashina et al. At ACL 2020. The second one is document ranking, and the third one is question answer. So let us look at a specific example. So first, let us say in a question answering system. So by uh, by Lou Pramanik et al. At SIGA 2019, the system is named as Quest. So where in response to a question, which country borders Mali and Ghana? So the ranked list looks like something like this. So the first rank contains 2 answers, the second one contains 20 answers, and the correct one is present in the fifth rank. Okay, so here are the number of entities present in the rank, each rank. Okay, so if we ignore them, so then heat at 5 measure will be 1. And reciprocal rank will be 5 because the correct answer is present at 5th rank. Okay, so next is we break the tries arbitrarily. So then also the heat at 5 will be 0 because before 5, 24 entities were present. And reciprocal rank will be, either 1 by 25 or 1 by 26. The third one is that most justified, evaluation protocol, that is expected values under random price. So this was done by McSherry and Nard at ECI 2008. So here also the heat at 5 will be 0, but reciprocal rank will be 1 by 25.5. So in this small example, you really cannot observe the differences, but we'll show you the empirical results. So the prior work by McSherry and Nard, they proposed the popular, tie versions of popular evaluation measures like precision, recall, F1, AP, reciprocal rank, and indices. So what's missing there? So hidden K is missing, and we fixed a wrong implementation of reciprocal rank. So let's look at mean reciprocal rank. So mean reciprocal rank is the average of all the queries of 1 by RQ. So what is 1 by RQ? So RQ is basically rank of first correct answer for the particular query. Okay. So now tie-aware reciprocal rank looks like something like this. So where in the first rank you have N1 entities, the second one you have N2 entities, the I-1th position you have N-1 entities. So that is in capital Ni-1 is basically sum over J running from 1 to I-1 in J. And your first correct answer, say, present in this ith position. So now in the ith doc looks like something like this. So first correct answer could be in the first position, could be in anywhere in lth position, or it could be in the N-K plus 1. So that is the worst case. So the expectation value will be basically we are summing over all the positions, that is L running from 1 to N-K plus 1 times L times probability of observing the first correct answer at Lth position. Now what is this probability? So this probability will be, so how many ways we can choose the correct answer and this Lth position. So we have K correct answers in this block. So this we can choose in K ways. And this remaining Ni minus L entities can be arranged in Ni L minus L ways. And here, so we can choose from basically the incorrect answer, that's Ni minus K permute L minus 1. That is this. And the denominator will be all the Ni minus 1 can be arranged in Ni minus 1 factorial. So this is our reciprocal rank. So next look at tie our heat at K versions. So here, for sake of the simplicity, we are looking at heat at 5. So here the setup is as same. So in the first, correct answer is present in this block. So and ni minus 1 is basically less than 5. So in the traditional definition of heat at 5, so where if your correct answer or correct entity is present within the 5 or top 5 rank list, you'll reward it as 1, otherwise 0. So here we are, trying to see probability that at least one correct answer. Okay? So that is 1 minus the probability that all positions are occupied with the wrong one. Okay? So here all positions are occupied with the wrong. How it can happen? So that is 1 minus. So we have n minus of k wrong answers. This is ni minus k. So from there we are choosing this 5 minus ni minus 1. So that is permute. And this rest, that is ni, so this is a capital Ni minus 5. These entities can be rearranged in ni minus 5 factorial ways. And then the denominator can be arranged in ni factorial. So this is our tie-aware measure for heat at 5. So as we can see, if we instead of 5 we have k, then we can simply just change the 5 to k, and we can get the tie-aware heat at k. Now we did some empirical observations. So what we used the datasets from West QA question answering dataset that was published by Liu et al. At SIGA 2019. So there they used two datasets, two questions basically, CQW and CQT, 150 complex questions each, and the top 20 documents retrieved for each query by Google Web Search. So here is the empirical observation. As we can see, so here we can see that metrics are MRR, where ties are ignored, and second one is random MRR, so where arbitrarily we are picking the ties, and the third one is optimistic, so where your for all correct answers are present in the beginning of the rank list, and pessimistic, your basically your correct answers are present in the tail of your rank list, and TIR award evaluation measure. And then we can see the Machine-Arcs implementation. So we can clearly see that MRR, if we ignore the ties, it's very overestimated values for all those two data sets, CQW and CQT. And also for heat at 5 also, we can see that same difference. So with our approach, we can see more principled ways we observe how to break the ties, and empirically also we observe this is more justified. So and these were references, and thank you.